recall that there are four basic categories of cash flows: lump sums, annuities, mixed streams, and perpetuities. We've already discussed the lump sums. Now let's discuss annuities. An annuity is a stream of equal periodic cash flows. These can be either inflows or outflows. An ordinary annuity is an annuity which the cash flow occurs at the end of each period, while an annuity due is an annuity in which the cash flow occurs at the beginning of each period. If you've had a car loan, you've had an ordinary annuity. In that car loan, you had a positive cash flow at the beginning of the loan, this is the amount that you borrowed, and a series of cash outflows at the end of each month. Those are those monthly car payments, and all those car payments are the same. So a car loan is an example of an ordinary annuity. A house loan, your house mortgage, is an example of an ordinary annuity. An example of an annuity due would be a lease. So if you have a car lease, you make that lease payment at the beginning of the month. If you have an apartment, that you make that rent payment on the apartment at the beginning of the month. So you've experienced annuity dues as well. The future value of an annuity due is going to be greater than the future value of an ordinary annuity because the cash flows occur at the beginning of each period, so there's more time for compounding. Likewise, the present value of annuity due is always going to be greater than the present value of an equivalent ordinary annuity because the cash flow occurs at the beginning of each period. There's one less period of discounting. So which of these are examples of annuities? Well, let's look at ordinary annuities first. Car payment, as we just discussed, is an example of an ordinary annuity. As are house payments. Those are examples of ordinary annuities. An annual $1,000 contribution to a retirement account, this would be an example of an annuity. If it occurred at the beginning of the period, it would be annuity due. If it happened at the end of the year, it would be an ordinary annuity. Lease payments, that would be an example of an annuity due. Your electric bill, unless you have some kind of special setup, that electric bill, the amount of the bill changes each month. So that's not an annuity because to be an annuity, the payments all have to be the same. A lump sum, well, it's a lump sum. It's not an annuity. Annuity is a series of equal payments, so it's not a lump sum. And variable interest received on a bank CD, well, the word variable, it's, again, an annuity due or ordinary annuity. Both types of annuities, the payments have to be the same in each period, so it's not variable interest. Let's compare an ordinary annuity and annuity due. Annuity A is an ordinary annuity, and we can see that the annual cash flows are occurring at the end of each period. So we'd have the beginning of the time 0, and at the end of the first year we'd have a $1,000 cash flow, second year $1,000 cash flow, so all the cash flow is the same. So we have a total of $5,000 in cash flows. Annuity B, our annuity due, we still have 5 cash flows, 5 years worth of equal cash flows, but now that first cash flow is occurring at time 0 at the very beginning, and in year 5 there's not a cash flow. So both of these are 5-year annuities of $1,000, so we could call them 5-year $1,000 annuities. One is an ordinary annuity with the cash flows occurring at the end of the period, and one is an annuity due with the cash flows occurring at the beginning of the period. Let's look at these a little bit more in depth in a spreadsheet. So this is our annuity due in the previous slide. If we calculate the present value of the ordinary annuity, so we're going to find the value at time 0, the present value. By the way, in Excel, and I strongly recommend that throughout all the lectures you open up the Excel spreadsheet that accompanies each lecture in case you can't really see the cells that clearly in the video recording. But one thing you can do is you can click on the equal sign anytime there's a cell with a calculation, and we can see we have the present value formula that's in Excel, PV. Notice I've got the minus sign in front of it because the series of cash flows in this ordinary annuity are positive. Excel will report a negative value to reflect the cash flows. In other words, if you were going to receive $1,000 each year for 5 years, you would have had to have invested some amount, a present value, at time 0. So I just put that negative sign just to get rid of the negative sign that it would have reported if I wouldn't put a negative sign in the formula. Also, you can see that up here in blue we have C4, So it's asking for first the interest rate in red. Up here this is in red, and we go down to red, it's asking for the number of periods, and then we can see the purple C3, that's the amount of the annuity, and then Excel will calculate that present value. Likewise, for the future value, and this occurs at year 5, again I'm going to click on the equal sign so that I can see the Excel formula FV. Again, the minus sign there just to account for the cash flow so that the reported value has a positive sign. So that future value is equal to, again, C4 in blue, 8%. C5, it's asking us how many periods. And then C3, how much is the cash flow in each period. And we do the same thing for an annuity due. And here I'm just going to work this out manually in this particular cell. There's also a PV function, but just want to see how we would do this by the formula. So it would be D8, which is our $1,000. And notice, let me click on this so we can see the colors. So the first one is D8, and notice there's no discounting there. We're not dividing it by 1 plus the discount rate. D9, this would be the first year's cash flow, and we divide that by 1 plus the interest rate of 8%, C4, raised to the power of 1 because we're discounting one period from period 1 to period 0, the present time, t equals 0. And then we have D10, this is the cash flow in the second period, and that's divided by 1 plus the interest rate raised to the power of 2 to reflect the fact that we have 2 years out. And then D11, that $1,000 cash flow in year 3, divided by 1 plus the interest rate raised to the power of 3 because we're discounting 3 periods back to time 0. And then finally D4, that's the cell here, that's that 4th year payment, and that gets discounted 4 periods for a present value of $4,312. And then I'm going to get a little bit lazy here with Excel. If you look at the formula, let me click on that so you can see. Excel has a formula FV, and if I put in at the very end a 1, that tells Excel that it's an annuity due. So if you didn't put anything here at all, then it would be treated just as a ordinary annuity, but with Excel I just put that in there to treat that as an annuity due. Now, while that's a nice feature, it's not exactly necessary. So for example, if you look here in column E, if I was to compare the value, the present value and the future value of an annuity due to an ordinary annuity, in other words, what percentage they're different, so the annuity due divided by the ordinary annuity and then subtract 1, that would be the same thing as looking at the percentage difference, annuity due minus ordinary annuity divided by ordinary annuity. We see that the present value of an annuity due is 8% larger than the present value of an ordinary annuity, and the 8% is our interest rate. So the present value of an annuity due is always greater than the present value of an equivalent ordinary annuity by the amount of the interest rate, 8% in this case. And that is because we have 1 period less discounting. Recall that first annuity due cash flow of 1,000, it's already at time 0, so there's no discounting. That's where that 8% comes from. Likewise, if we look at future value, we see that the future value of an annuity due is 8% larger than the future value of an ordinary annuity. So the future value of an annuity due will always be greater than the future value of an ordinary annuity by the amount of the interest rate, in this case 8%. Let's work through an example with payments. You've probably noticed that unlike the lump sum where we had the formula for present value and then we rearranged that for future values for the number of periods or the interest rate, I didn't show the equation for the payment. And the reason for that is that the equation for the monthly payments, it's got lots of parts and it's a pain to calculate. Let's just use Excel or calculator to do that payment. So let's do an example of a mortgage. So this would be an ordinary annuity, and let's say you borrowed $75,000 at an interest rate of 12%. So we need to calculate a monthly periodic rate, and we arrive at that by simply taking the nominal annual rate and dividing that by 12 for 12 months in a year to arrive at a 1% interest rate, and we call that a 1% periodic interest rate. Interest rates are always reported in nominal annual terms, the 12%, but since we have monthly payments, we need to calculate the monthly periodic interest rate. Number of periods, well, there's 30 years. That equates to 360 months, so 30 times 12. And the future value, well, we're going to pay off this loan, so the future value of the loan would be 0. We can use Excel's payment function, the PMT, to calculate the amount of this ordinary annuity payment, the amount of the house payment. So that's going to be a function of the blue, the monthly interest rate, the red here, D5, the number of payments, and the amount that was borrowed, C3. And we come up with a payment of $771.46. Now I notice that I didn't correct for the negative sign here. So what this means in Excel is you borrowed $75,000, so you had a $75,000 cash inflow, but you're going to have payments which are cash outflows, and that negative sign reflects those payments. So our payment with an ordinary annuity is $771.46. But what if this was an annuity due? Well, Excel, if we put a 1 at the end of the payment function, as you can see right here, it will calculate an annuity due for us using the same interest rate, number of periods, amount borrowed, and future value. And we see that the payment is only $763, so the payment for the annuity due is less than the payment for the ordinary annuity. In fact, if I look at the percentage difference, so I calculate the annuity due divided by the ordinary annuity minus 1%, we can see that the annuity due has a value that's of 99.01% of the ordinary annuity, or if I want to calculate that, I'll just take the inverse of 99.01%. The annuity due payment is smaller than the ordinary annuity payment by 1%. That 1% is exactly equal to the interest rate. So the payment of an annuity due is smaller than the payment of an ordinary annuity by the amount of the interest rate. To demonstrate that, I could have simply taken the payments to calculate the annuity due payment. I could have used the ordinary annuity payment of $771.46 and divided it by 1 plus the interest rate, 1 plus 1%, or 1.01, and came up with the exact payment as I did with the Excel payment function of $763.82. So to recap, the annuity due, future value, and present value will always be larger than the present value and future value of an ordinary annuity, but the payments to an annuity due will be smaller than the payments for an ordinary annuity, and the difference is the amount of the interest rate. Let's wrap up with one more practice example. How much must be saved annually beginning 1 year from now in order to accumulate $50,000 over the next 10 years, earning 9% annually? We can either do this in Excel or via financial calculator. Let's work this one in the financial calculator. We're not given a present value, so we're assuming that is 0, so 0 present value. $50,000 future value. Again, with the financial calculator, it's the number and then the input on the time value of money row. We had a 9% interest, so 9 and then interest, and then we had over 10 years, 10 and then N, and then hit compute payment, and our payment is $3,291. Notice the negative sign reflects that this is a negative cash flow. We would have to invest this much each year for 10 years, earning 9%, so that in 10 years we would have $50,000. Again, as a reminder, before you start any problem, be sure and hit second, clear time value of money, and then clear your memory at the bottom prior to starting any problem.